We've got a number of folks out today, and so for those folks that are out, I am going to be making a recording today for posterity's sake. This will let them go back and kind of get the information that they're missing a little bit later. So, by definition, this is what I want to make sure we got into your notes today. Also, be careful what you're saying, because it will be recorded, and should there be a dispute later, it's just recording.
Okay. What should we title for now?
Limiting reactants. By definition, a limiting reactant is the reactant that runs out first. I like to call the limiting reactant the boss. The boss, because it's in charge. It's in charge of the reaction, because once you run out of the boss, your reaction stops. Your reaction can no longer proceed if you run out of a substance. By definition, limiting reactant is the reactant that runs out first. It determines how much product you can make. Well, we should probably talk about excess reactants then. If limiting reactants are the reactants that run out of first, what does that mean for the excess reactants? These are the leftover reactants. We could also call that the unused reactants. This is the substance that you have in excess or an abundance of. You're not going to use it all up. You're not going to use it all up. So if we were to look at an example, hydrogen and oxygen react to form water. You start with 10 moles of hydrogen and 7 moles of oxygen. We want to know how many moles of water will form. Now, according to a reaction, we got to have two things. We got to have some hydrogen. We got to have some oxygen. They have to react together. When they do, they explode incredibly violently. I actually went to do this demo last year down in the Common Arts area, because that's where my room was last year. And I tried it before school started. And it exploded early, and so it blew up in my face, and I actually had ringing in my right ear until lunchtime. I did it wrong. Like I didn't wait long enough to actually start the reaction. I'm going to try it again for you guys on Friday. I hope we'll try this, see how the synthesis reaction goes. It's a good one. It's really cool. But this is actually one of the ways they think that water first formed on the planet, as the different gases kind of combined out of the nebulous that formed our solar system. The hydrogen and oxygen got pulled towards planet Earth, and then the static electricity that built up as a result of all these particles rubbing on each other created a spark that then ignited the hydrogen and oxygen gases. So that's one of the ways they think water formed on the planet. So we're going to look, our oxygens react with the hydrogens to start forming water. They all react. What got left over here? The oxygens are in excess. Are there any hydrogens? Are there any of the white pairs just floating around by themselves? No. No, they all got used up. That makes them the limiting reactant. Now, here's the deal. I love today because we're not doing anything new in terms of the math. You have all of the skills that you need. And in fact, this is going to help us review them even more. Don't get mad at me. Or if you do get mad, don't tell me. If I gave you grams of some stuff, you could change it
into moles of some other stuff.
Yeah, I put this on the board like every day for 3 weeks now. So if you're still having trouble with this, come and see me. We got to get it shorted up. Change it into moles of other stuff using molar mass of that stuff. We can change moles to moles of A to
Moles of B.
Moles of B using mole ratio.
Ratio upward.
Mole ratio. Where's the mole ratio come from again?
Balance.
The balanced chemical equation. Then if we need to, we go moles B back to grams B using the molar mass of substance B. I'm abbreviating molar mass, MM, molar mass. Well, MR, mole ratio. How we doing? I love it because we have been doing a bunch of these and we don't have to worry about anything new. We're going to continue to use the same skills we've already developed. We're just going to think about it and use it in a slightly different way. Really, we're just going to do it twice instead of once, which ain't so bad. Can we look at an example? Grab your, is it okay if I do some of the homework with you?
Oh, no, not anymore.
Okay, notes go away. We're done notes. Grab the hand up. Numero uno. Number one. Consider the following reaction. Oh, that's nice. It's the same reaction still. We've got two hydrogens reacting with one oxygen to form two waters. Letter A says we've got 50 molecules of hydrogen, 25 molecules of oxygen. Identify the limiting reactant, Dabao, in each of these reaction mixtures. We will sometimes abbreviate limiting reactant LR. Okay. Limiting reactant LR. Cool. All right. Ooh. Ew.
What?
Where are molecules on our train? It's on the old train, but how do you go from molecules to moles?
Using mole ratio.
Oh, God.
6.02.
6.02
I thought
times
that was
10
ratio.
20 30.
Oh, that's why you're sticking.
Right? Now, wait a minute. To go from molecules to moles, isn't it the same number? 6.02 times 10 to the 23rd? Yeah. If you remember, back when we first started talking about these balance equations, didn't we say this 2 means we got 2 molecules of hydrogen reacting with 1 molecule of oxygen to form 2 molecules of water? Back in the day, weren't these molecules? And then we said, well, molecules really little. We're going to use moles of them because we need a lot of them. Right?
Yeah.
Can I make it simple for us? Molecules and moles are interchangeable. If you're talking about a bunch of molecules, you're going to use moles. If you're talking about just a couple molecules, you use molecules. But really, they mean, for our purposes, the same thing. We could consider them 50 molecules or 50 moles. It's going to be the same ratio to change in between them. To go from molecules to molecules or to go from moles to moles, we're going to use our ratio. And the ratio again comes from
Mole.
the balanced chemical equation. So when we have a problem, what do we always start with?
What's given?
Reset.
What's given?
You always start with your given, right? This is old news. So we've got 50 molecules or moles of hydrogen. There's one of our givens. Oh, we also have 25 molecules or moles of oxygen. Okay. What does a limiting reactant do again? Limits what? It runs out first and limits what? How much product? What's the product in this reaction? The water. Well, let's solve them both for moles of water then. How do you go from moles to mole? Well, ratio. What's your ratio for hydrogen to water? 2 to 2. For every 2 moles of hydrogen, we got 2 moles of water. Do not use your calculator. What's 2 divided by 2? 1. What's 1 times 50?
50.
Good job. See, you didn't need calculator. We get so dependent on our calculator. Oh, I gotta put this in my calculator, and they're like, oh. Try something.
Just to be sure.
What's our ratio of oxygen to water?
1 to 2.
1 to 2. Where are you putting 1?
On the bottom.
On the bottom, for every 1 mole of oxygen from our balanced equation, for every 1 mole of oxygen, we're going to make 2 moles of water. 25 times 2?
50.
50. Ooh, okay, so which one made less product? Oh, so who's limiting? Neither. Oh, that's nice. Now, wait a minute. What do you know about molecules? Huh? They're everywhere? Some come in pairs. Not all. These ones did. Just in terms of their size. Molecules are tiny. Can't see them with our naked eye. How would you count out 50 molecules? Yeah. This is a nice math problem, but you couldn't actually do this in real life, could you? Count out 50 of one and 25 of the other and then make them react in this teeny tiny react? No, I can't do that. We use moles, which means the chances of getting it perfect like this, pretty slim to nil. Let's try this second one here. B. We've got 100 moles of hydrogen, 100 moles of molecules of oxygen. Find the molar reactant. Well, start with given. 100 moles of hydrogen. 100 moles of oxygen. What do you want to solve for? Moles of water? Sure. Wait, isn't this the same as what we just did? Okay. How do you go from moles of one thing to moles of something else?
Mole ratio.
Mole ratio. What is the mole ratio for hydrogen to water?
2 to
Hydrogen to water is
2.
2. 2 divided by 2 is 1 times 100 is 100 moles. So here's the deal. If all of the hydrogen reacts, it could make 100 moles of water, but it has to react with the oxygen. Well, let's figure out how much water our oxygen can make. It's like, here's your bread, here's your ham. Let's figure out which one gets used up first. Just solve them both for the same product. Well, how to go from oxygen to water? Mole ratio is
2 to 1.
2 over 1 for every 2 moles of water on top. We got 1 mole of oxygen on bottom. 100 times 2? 200. Well, riddle me this, Batman. Will we ever make 200 moles of water? No, we will never be able to make this, because what will happen before we make 200 moles of water? Our hydrogen will run out. By definition, your limiting reactant, is the substance that makes the least amount of product. We're only going to be able to make 100 moles, because then we run out of hydrogen. And then our reaction stops. How we done?
Good.
Feel okay? I love it because in terms of the math, we're doing the same thing we've been doing. All we're doing is we're doing it at the same time to be able to compare them. So it reviews the stuff we've been doing, makes us think about what's actually happening in our beaker or in our flask. These two things are coming, they're reacting together to form some stuff. Now we can say which one makes less. Letter C?
Sure.
Okay. Well, letter C. What do you start with? Always. In the words of Sandlot, forever. Always start with given. We've got 2 givens here. What do you want to solve for? Moles of water. We're getting a little redundant now, aren't we? Good thing this is the third part, and then we'll go this type. Alright, moles to moles we use.
Ratio.
Mole ratio, hydrogen to water is
3 to 1.
2 moles of hydrogen. Got 1 mole of water. Wait a minute. Not 2 to 1, it's
2 to 2.
2 to 2, isn't it?
I was trying to tell you.
It was a test, right? You were testing.
Yeah, I was seeing if you know.
Seeing if I was paying attention.
Yep.
0.8 times, what 2 divided by 2 is? 1 times 0.8. 0.8. So if all of the hydrogen reacts, it'll make 0.8 moles of water. What's our ratio oxygen to water?
2 to 1.
1 to 2, where you put your 1? 1 mole of oxygen. 2 moles of water. You're gonna end up making 0.75 times 2.
That's 1.25 or 1.50.
1.5. Okay, how much are you actually gonna get? 0.80. Who's your limiting reactant then? Hydrogen is your limiting reactant. This is a great example of one of those times. We started with less oxygen here, right? We had 0.8 hydrogen, but 0.75 oxygen. We had less oxygen, but we ran out of hydrogen first.
How did you get 0.8?
So because it's a 2 over 2,
Oh, it's
1, so 1 times the number is that. Yep. How we doing? Can we try a trickier one? I'm going to jump just a little bit. Let's look at number 3. Number 3, Melissa. Yeah. We got the movie. Sure. Number 3. When you pass ammonia over solid copper 2 oxide, the products are nitrogen gas, solid copper, and water vapor. Ooh, we need our recipe. We need our ratios. We need a balanced equation. Ammonia is NH3. If it's gaseous, what's the state symbol? G. Reacting with solid copper 2 oxide. Ooh, what's the 2 mean? Charge in the copper is 2 plus. What's the charge on an oxygen? 2 minus. They add together. 2 plus 2 minus.
Yes.
Plus 2 minus. Yep. They said this was solid, so it gets a little S state symbol. These are reacting to form some products. Our products are nitrogen gas with a nitrogen symbol. But it is diatomic and off wrinkle. It's gas room temperature. Floating around the room right now, about 80% of the room right now is full of nitrogen. Doing nothing. Great, and they're fairly inert. Making some solid copper, going to be with an S. And we've got water vapor. Water vapor being H2O in what state? Vapor?
Oh.
Gas. What's the last thing when you do here? Ooh, alright. Somebody gets it, let me know. Put it up.
Two, three, one, three, three.
It says 2, 3, 1, 3, 3. Sound good. 2 nitrogens, 2 nitrogens, 6 hydrogen. 3 times 2 is 6 hydrogen. 3 copper, 3 copper, 3 oxygen, 3 oxygen. Next. B says you've got 15 moles of ammonia, 15 moles of copper 2 oxide. We got 15 moles of both of these. We need to figure out which is the limiting reactant. By definition, what does the limiting reactant do? Limits what? The products. Ooh. How is this one different than the one we just did? How many products are there? There's 3 products. Womp womp. Wait a minute. A limiting reactant limits the amount of product produced. Does it matter which product? No. So long as you solve both of them for the same product, whichever one makes less is going to be your limiting reactant. It doesn't matter if you solve for nitrogen or copper or water. Whichever one you solve for, just make sure you solve them both for the same one. Do you guys have a preference? Do you want nitrogen, copper, or water? Nitrogen?
Yeah.
I heard nitrogen. Makes sense. This number's a 1, isn't it? Gonna make the math a little easier. Cool. Yeah, so let's solve them both for moles of nitrogen. Again, it doesn't matter which one you solve for. so long as you solve them both for the same product. You can't compare them unless they're the same product. Well, moles to moles we use ratio. What's your ratio? Ammonia to nitrogen. 2 to 1. Where you put your 2? Bottom of 2 moles of ammonia. 1 mole of nitrogen. 15 divided by 2. 15 times 1 is 15. Divided by 2 is 7.5. Maybe we'll make 7.5 moles of nitrogen. Maybe we won't. Depends on my copper to oxide. What's our ratio? Sorry, keep the color sharing. What is our ratio for copper to oxide to nitrogen?
3 to 1.
3 to 1. We're putting 3 top bottom. So 3 moles copper to oxide. We make 1 mole of nitrogen. Ooh, what's 15 divided by 3? 5. Can I be like super nitpicky? How many sig figs? 2. How many sig figs? 5.0. Yeah, if we're being like super nitpicky, 5.0. Again, I think I shared this. We're kind of stepping back in sig figs, but it's still good if you kind of carry those through. How much nitrogen are we actually going to be able to make? 5. We will never make 7.5 moles of nitrogen because when we make 5 moles of nitrogen, we run out of
Copper oxide.
The copper to oxide is our limiting reactant. It does not matter which one you solve for so long as you solve for the same one.